Hello everyone, welcome to week 9. Uh, this is week 2, like second week for network flows, and we have studied min-cut theorem, duality of max flow and min-cut in this week. And today we are going to solve one problem related to that. So I've already put this on GitHub. Let me share the link with you. You can open the link, or I'm going to also open the PDF file here. So let's take a few minutes to read the problem statement. Okay, I hope you have read the problem. So I forgot. Yeah. So I hope you have read the problem. So the problem is that you are given a grid of size n cross m, where every cell in the grid has a value Vij. Now you can basically pick the value in that cell, and for the cost of picking that value is Cij. But if you pick first all of its neighbors, which are the like up cell, which is just above any cell, like basically the four cells on the four sides, then if you pick all of those cells first and then pick this element, middle element, then you are going to only pay Bij, where it's already given that Bij will always be less than Cij. So you are always going to pay less if you pay, if you're always going to pay less if you first pick the neighbors, all the neighbors, and then pick the middle one. And so you have to pick all the four neighbors first, okay? And then your score is the sum of the values that you have captured minus the cost it took to capture those squares, and you have to maximize your score, okay? And the constraints are, there are three subtasks in this problem. First is when n and m are less than equal to 3, then Second subtask is nm less than 7, and then final one is less than 25. Value of the elements is less than equal to 10 to power 5. Okay, and there is at least one cell, nm greater than equal to 1. So, and the input will look okay, there is, I forgot to add an example here. Sorry, it seems to not, my cursor seems not to be working. Okay, so first of all, I think how will you solve this problem in a very brute force manner? It's working now. So for the first subtask, 1 n and m are very small. So do you think you can solve this in a very naive manner, and what would that be?
I think we can try all sorts of possible routes in which we'll try to capture the cells, and then we'll check what will be the value that we get and compare the best that we get.
All your first line was we will get all.
All possible patterns of capturing the cells.
um, I think that corresponds to the permutation and also how many numbers are captured.
Yeah.
Yeah. So will it work for n and m less than equal to 3? Will it also work for n and m less than equal to 7?
I think it should work for n and m less than 7,
Okay.
but
And
I don't think it would work well out for 25, because that would be too large, because we have vertex of order like 625 or so.
mm-hmm.
So that's why it will work out for that. For 49, I think we can make up, because we'll have around 10 raised to 5 around parts or something only. If I take roughly, I'm not sure.
Paths,
Parts I means permutations, like
permutations.
the patterns, yeah, how we capture results.
Hmm. Hmm. So, but if you have 49,
Yeah, I don't think 49 would also work. That would
yeah,
also be large.
yeah, it's a
49.
pretty
Yeah,
large number. Yeah,
49 factorial would be like,
yeah,
so that would
it's,
be too large.
yeah,
I think it will work only for 3, I guess.
yeah,
Yeah.
yeah, yeah. So the permutation is important because of this condition that when you are picking a cell, if you have not picked its neighbors, then you have to pay Cij. But you have picked all of its neighbors, then you pick Bij. So that's why the permutation is important here, and not just how many cells or which cells you are picking. And 9 factorial is small, but 49 factorial is a very big number. So you cannot, even in that, like first case, it is not 9 factorial. It is like the first case is when you pick you capture all the cells. Then it is 9 factorial base. Then if you say that no, I'll pick only 8, then it will be a 8 factorial base. Or, and when you say that I'll pick only 7, then there's 7 factorial base, right? So that is also not just 9 factorial. So you can solve the first subtask with this naive approach, but that is not enough. I hope the naive one is clear.
Just one thing.
Yeah.
When we will be calculating those 9 factorial ways, won't the initial ways be same as the other ways? Like, if not choosing the last element, we are already choosing the first 8 elements, and we can have like a counter running while capturing those 9. permutations of 9.
Yeah, I mean, we can save if we do it in a intelligently. Then I think we can. Uh, yeah, we will not have to redo the computations again.
Yes.
Yeah, but that is, yeah, if we do it intelligently. That's, yeah, you are right about that. Hmm. Okay, so now let's focus on the problem and like what will be the solution, optimal solution that will work here. I mean, we try to understand the problem. So we know that this problem is network flow problem. We have to uh, I mean, because we are solving in this week, so we know that the solution is most likely a network flow, and so we now need to model this as a flow graph, which is the hardest part or the most important part. So here we now first need to decide what will be the vertices of the graph, and then what will be the edges and what are the edges going to denote. I think these are very important questions that we need to answer. So do you have any ideas what will you choose the vertices as?
I think we'll choose the cells of the matrix as the vertices, and we can assign a start vertex or and target vertex differently. That will map to every cell, I guess,
Mm-hmm.
because we can start from anywhere and anywhere. So like that.
Yeah.
And for edges, I'm not sure. Just thinking about it. Okay.
Okay, I'll just draw what you are telling me so that we will then. So this is, let's say, our grid, and I will just name all the cells in it. I hope it is big enough. So these are our vertices, and then there is one vertex S start and one vertex D here. And then what about the edges?
I think first of all we'll connect S to every other vertex except for T, and T also for every other vertex except for S.
Okay, so we are going to connect every vertex to S and T in
Yeah.
like this. Sorry. Okay, 1 second. Let me use some other color for this. Now, what does your edges represent?
For me, I think I mean we can just choose a path like the way we are trying to go from starting to end. So choosing the edges, we are kind of paving a path like where we are going, or the way we are choosing the uh, vertices.
Hmm.
And I'm confused about that only right now. Like, how we use the min cut to find like the best possible score that we'll get.
Yeah, yeah. So here, let's simplify the problem. So if the problem asked us that you can either pick so problem like very simple, that you can pick a cell and pay Cij, or you do not pick the cell. And if that were the case, there is no concept of direct indirect, and there are only two choices: pick or not pick. Then in that case, I think this works. I mean, that is of course very easy also, we can just solve it. But this also I think will work, because here let's say the first edge, black edges, they will represent, let's say, pick, and the red edges will represent don't pick. And when you take a black edge, then you are going to pay a cost which is equal to Cij. And let's say not talk about the cost, but like do you agree that we can pick only one of these edges? We cannot pick them both.
Yeah.
And that is what we want to ensure, that we should be able to make only one action, and that is of course happening here. And another thing is that if we now take a cut of this, that so then the minimum cut will actually be our optimal answer. Now before that, I need to of course tell what will be the weights of the edges, what do they represent. So let's say that so here we are thinking about the problem in terms of both things: what do we earn and what do we lose. Like whenever we are going to pick a element, we are going to get Vij, but we are losing Cij. Now let us just model this by saying that whenever we don't pick an element, we are losing Vij, and whenever we are picking an element, we are losing Cij. I'm repeating. So whenever we are going to pick a cell, we are losing Cij amount, and whenever we are going to not pick a cell, we are losing Vij, the value of that cell. Okay, so then if we give the black edges, where black edges are pick and these are not pick, and the weight of these edges will be the amount we lose. When we pick, we lose Cij, and when we not pick, we lose Vij. I hope, I mean, I'm just calling them Cij, Vij, but you can associate them with the cell number. Now, since every edge is denoting the amount you are losing, so you need to minimize your loss. So that will be now equivalent to the minimum cut. Does that make sense?
That makes sense, but what about the Bij that we were talking about? Like, we'll have to connect them to also the adjacent vertices, right?
Oh, this is not for the original problem.
Okay.
It will definitely not work there. I'm just saying, let's say if we had only two actions to perform, we could perform only two actions. One is either pick cell or don't pick the cell. Okay, so
Yeah.
if you are picking the cell, then you are losing Cij. Assume that, so what is the total profit what is the total value that you can gain. Total value that you can gain is the sum of all the values in the grid. That is what you can gain total. Now whenever you do not pick a cell, you lose Vij minus Vij from that. Let's call the total amount that you can, total value of the grid is V. This is the total value of the grid. So whenever you are not going to pick a cell, let's say you don't pick any cell, then you will subtract every cell value. Whenever you choose all of these red ones, you are going to subtract every Vij from capital V. So your profit is 0, or you can say that your loss is capital V. You have lost this much amount that you could have gained. Or now here, but in this graph you want to minimize your loss, so you will pick some elements and you will not pick some others, which is very easy here. You will always pick the smaller one. Now coming back to the original problem, so this is not enough. Why? Because we do not have only 2 actions, we have 3 actions. We have to either pick directly, pick indirectly, or not pick. And every edge can be associated with only one action type. So we need at least 3 edges for every cell. So then what do we do? Let's so we need 3 edges, and so then we need to introduce new vertices. Let's call these new vertices as copy of the cells. Now why do we need copies? Because we cannot add more edges between say C1 and C3. That because it is not a dependency action, like capturing directly, capturing indirectly, and not capturing at all. All of these are only for that cell, and they should not affect the other cell. Whether I capture this cell or of course it does, I mean later, but for now simply it should not. So then let's say as before, these are our edges from this one edge from every Ci dash to T, and then edges between these pairs also. I'm using different colors for different type of action. So black, let's say the black color is representing here capture directly, and red is representing capture indirectly, and the green one means don't capture or ignore. Now what will happen in this? If we find the min cut here, again so what will be the weight of every edge? With what we have discussed right now, this thinking in terms of losing. So what will be the weight of the direct edges, indirect edges, and ignore edges?
For direct edges, I think it would be like what will be the value that we gain if we take it.
Hmm.
And for indirect, it would be like what will we lose of the total gain that we can have, right? And for ignore, uh, I'm not sure about it. I'm currently thinking about it, right? Yeah.
Okay. Yeah. So here, actually we are saying that whenever you don't capture a cell directly, then let's say that means that you lose Cij value. Whenever you capture the cell indirectly, you're losing some amount, right? You lose Bij. We are not talking about what you're gaining. It's not writing, it's writing above. Sorry. And whenever you are going to not capture that cell, you lose its value Vij. And we want to minimize our losses, and that will maximize our profit. Finally, we are going to subtract our losses from the total value of the grid. So think of it like this, that you have in the grid every cell. For every cell, if you don't capture it, you will minus Vij from the total value, capital V, which I said that capital V is equal to summation of Vij for I is equal to j is equal to 0 to I is equal to n, j is equal to m. Okay, so this is your total value of the grid. For every cell, if you do not pick it, if you do not capture it, you subtract Vij. If you captured it, you captured it directly, you subtract Cij. If you captured it indirectly, you subtract Bij. Now we are talking, so how will you maximize your profit? By minimizing your losses. Now we are talking about in terms of losses. We want to minimize our losses, and every edge is going to represent you the quantity that you lose whenever you choose that edge. Okay, so now can you try again that when you are going to pick a direct edge, what does that mean, and what weight will these, a direct edge, a indirect edge, or a ignore edge will have in this flow graph? So I hope that it is clear that we have these three types of edges because there are three types of actions. One is capture directly, capture indirectly, and ignore. And you can take only one action, and you should not be able to take multiple actions. Okay? And the weight of every edge is dependent on what kind of edge it is. So if it's a direct edge, I mean captured directly, if the edge is representing that capture the cell directly, that means you are going to lose Cij value. If you're going to ignore it, you are losing Vij. And if you're going to capture it indirectly, you're losing Bij. So these will be the edge weights. And the semantic with the edge weight is that is the quantity you lose when you choose that edge. So these are the vertices. The vertices are cells, and we have kept copies of them. We wanted to have different types of, like 3 different types of edges, and then we have one source vertex and one destination sink vertex. Now we are going to find here a min cut, but before that, so what will the min cut do? Min cut is basically going to minimize your losses here, because your edges are representing your losses. Now, if all of this is clear, then the question we need to ask is that is this satisfying all the conditions we are asked in the problem statement or not?
Ma'am, one question here.
Yeah.
Uh, we know that we can use the Bij value only. I mean, capture indirectly only when we have captured all the 3 cells around it, or all the 4 cells around it.
Yeah.
So how will we model that? Because we have not considered any relation regarding to that right now.
Yeah, so that is the next part that I was saying, that we have not satisfied all the conditions of the problem statement yet. Exactly what you said. Currently, in this graph, if we so the semantic I've given here is in terms of the colors, like black, green and red. So if you can pick some cell indirectly without ensuring that all of the neighboring cells are picked directly. So that is not being ensured here. We need to modify we need to model that condition in the graph. Next. Okay. I hope you got some time to think about that why it is not the case right now, and we need to model this. So yeah, so then there is some relationship between the cells, like C1 is, let's say, neighbor of C2 and C4. We need to add those relationships in the graph, right? And we can do that by adding edges, of course, between the cells. So that is one thing that we all agree. I mean, we of course need to add some edges here. Now let's say if we add the edges between the neighbors, so let me just see. I'll mark here in this. So I've marked here 4 red cells. So so think of this grid as a chessboard, because that will also make it easier. Uh, so C1 is a white cell, C2 is a black cell, then C3 is a white cell, and C4 is black, then white, then C6 is black again, and so on. Right? So a white cell is always going to be uh, like it is all of its neighbors are going to be black, and similarly for a black cell, of all of its neighbors are white, right? So if we talk in terms of like black cell and white cell terminology, then for a black, for this C5, we are going to connect it for every black, not C5, let's say for every black cell, we are going to connect to its neighboring white cells in this graph. So what does that mean? That this is our black cell here, represented by C2 and C2 dash. We are going to connect it with its neighbors by some edges. I should use different color. Sorry. And then C5. Okay. Similarly for C4 will be connected to C1, C5, C7. Same on this side, and then C6, C9, and then one left is C8. So I'm just going to leave C8 so that it does not become very cluttered also. So then let's say this is, we add these edges to in the graph to take care of the like the dependency, that which cells are neighbor of each other. Now in this graph, do you think that if we pick one for, can we take 2 actions, one cell now?
I think we can take 2 actions as well right now as well, because we still have those edges that we took for like the loss we are dealing with.
Mm-hmm.
The first will be the loss that we were having to like, if we directly capture it, so the cost, and then we still have that ignore edge from every cell to itself. So that would be like, if we indirectly capture it, that shouldn't be the case. We have to like make it a definite dependency, that we have to select all the other uh, vertices around it, then only we can use the ignore edge, something like that.
Mm-hmm. Yeah.
uh, and then we can obviously just connect it to the target to check the case for not taking it.
Hmm.
But I'm currently confused right here in the middle only. like we're not exactly setting up dependency. I mean,
Hmm.
yes, they have connections, but we can choose the cell after choosing any one of the adjacent, right?
We can choose the cell after choosing any one of the adjacent.
Vertex.
Example.
Like we have chose C2, then we can choose C3 as an indirect path,
Hmm.
and then we can go to like sorry. After choosing C2, we can choose C3, and then from C3 we can go to target, like something like that.
Yeah, and what will that give us?
I think for that it will give us like C2 will give the cost of sorry from start to C2 it will be the cost of choosing C2 directly, and then we can get the cost of choosing C3 indirectly, and then we can just go to the target for C6. It can be just like choosing directly, and then like we are going to C3, we can also go to C6 indirectly that way.
If we are going to c3, we cannot go to c6. How? I mean, the edge
It,
direction is
yeah, okay,
this.
direction is there, but that's where I'm getting confused. Like this
Yeah.
network.
Okay. So there is one more small part of it which is left, is that we need to swap the edges of the white vertices here. So that means these are, sorry, I need to change the color. Okay, I'm not going to do this for everything, every just maybe in the red I'll just do it. It may be. So what we are doing here is that we are swapping the type of the edge. So we are saying that the first edge, which is going from S to C, is a indirect edge, is a type of indirect edge if it is a white cell, and if it is a black cell, then the edge is a direct edge. Direct and indirect means capture directly, capture indirectly. Okay, and so now the graph is complete. Now here, whenever you're going to capture one, what are the constraints? What do we want? We want that every cell be captured only once. Direct, basically we take only one action on every cell. Capture directly, indirectly, or ignore. That is one condition. Second is, if we capture a cell indirectly, we need to ensure that all of its neighbors are captured directly. These are the two conditions. Now this flow graph need to ensure both of these conditions. Now let us see them one by one. So what does it, so for C1, if we decide to capture it indirectly, we are going to take edge E1, and then we should, if we are going to capture it directly and we say we take edge E1, that means we should, all of its neighbors which are going to have a edge to it, these blue edges, they must be captured directly. And when they are captured directly, these blue edges will basically have no meaning. because the black edges which are in the first half, this side, they will be cut. So you will not have any path. And basically you will not be able to take this green edge or this edge at all. Now, is this clear? Why did I make the last statement?
Can you please repeat the last statement?
Yeah, so I was saying that, so first there are two things that I am claiming, and so I'm not proving them, I'm just claiming that this graph is going to ensure that when you take one action for a cell, you cannot take the other action. Second one is that when you pick a edge, when you pick a cell indirectly, all of its neighbors will be picked directly. That will be ensured by the graph. Okay, so these are the two conditions. So assuming that the second is true, which I have not yet told you how, but let's say if one cell is picked indirectly, then all of its neighbors are going to be picked directly. Let's say this is true. Then in that case, if we take this edge E1, then it means all of the neighbors, which are the black neighbors like C2 and C4, it has only two neighbors, C2 and C4 here. So they must be picked directly because C1 is being picked indirectly. So these two black edges, E2 and E3, E2 and E3 will be cut. They will no longer be part of the graph. They will be cut as soon as we pick V1. Do you agree?
Yes.
So if the condition second is correct, that means condition 1 is true. Then you will not be able to take the ignore edge or the direct edge. That's the first thing. Now we need to ensure that whenever you're picking a indirect edge, its direct edges, the neighbors will, the direct edges of the neighbors will definitely be picked. That is the only part that we need to show, that will always be the case in this graph. Okay, so how do we show that? Indirect. Let's say this is the indirect edge for C2. Okay, that means we are saying that we are picking C2 indirectly. That means we must pick C1, C3 and C5 directly. Okay, so when we have picked this E4 edge here indirectly, so what are the relationships? Like C2 is connected to C1, C3 and C5 here. Right. So in that case, if we pick E4, the edge E4, which is the indirect edge from C2 dash to T, then if we do not pick the direct edges, so this is so let's I'm just going to say and I'll repeat. So if we do not pick the direct edges, let's call them E5. Its neighbors are C1, C3 and C5. C1, C3 and C5, yeah. So E5, E6 and E7. Let us say we do not pick. Let's say for simplicity, let us say we picked E6 and E7, the direct edges, and we have not picked E5. And instead, we are picking E1, which is indirect. Then what will going to be happen is that there will still be a path from S going via C1 to T, which can be S to C4, then C4 to C1, C1 to C1 dash, and then to T, because we in the first step did not pick E5. Instead we picked E1. And E5 is our indirect edge, Bij. This is our direct edge. Sorry, am I? No. This is our Bij. This is our Cij. So in the next step, if we picked E1 first, and then there will still be a path through C1 dash to T. Then in the next step, we will have to pick one more edge to saturate. Like there will be still augmenting path left, and we will, of course, our algorithm is not going to terminate unless all of the augmenting paths are taken. So there will be still one augmenting path left, and we will take that. And that is going to increase our loss, because now we are going to take E5 also, and we have already taken E1. Or they ignore. I mean, I am saying that will not be a min cut. And our algorithm is trying to find the min cut. So it will always choose the direct edge over the indirect edge, because that is optimal. So what I've said is that if and the graph is also very cluttered. So if we pick C2 dash, basically cell 2 indirectly, that is we have this E4 edge, we have picked this edge. Then basically let's we remove this edge E4 from the graph. Okay, after doing that, if there it has three neighbors, C1, C3 and C5, I'm saying that the algorithm will pick E5, E6 and E7, which are corresponding direct edges for C1, C3 and C5, because if it does not pick the direct edges, then it will not be a min cut. Because if it did not pick the direct edges, let's say it picked the ignore edge, C1 to Ci dash, then we can go from S to C4 to C4 dash, and then C1 dash, and then T. We will still have an augmenting path, which will increase the loss. And it will not be the optimal. So whenever it is going to pick an indirect edge E, like say E4, for the neighboring vertices, it is definitely going to pick the direct edges. So I'm just going to redraw the graph again because all of
Yeah,
the
one thing. So it's like first we took any of the let's say white cell, that is C2, C4, C6, and C8, any of those. Then if we are choosing the ignore edge, then we'll choose all of the other ignore edges as well, so that we can, because like the loss there is minimal compared to the uh, directly connected edge. So it will obviously choose that path for sure. It is like something like that.
if we are going to choose the ignore edge for which cell?
Let's say if we are choosing the ignore edge for cell C2, then we'll choose the ignore edge from C2 to C1. That will also has the weight of let's say uh, B11, because it is the ignore edge for C1 cell 1. So we'll choose the ignore edge from C2 to C1 dash, C2 dash for to C1 dash, yeah, this edge,
Um,
and then we choose
that
E5.
is so let's not call that ignore edge.
Yeah,
Ignore edge is the green edge.
okay, okay.
Let's call it
So
blue
from,
edge.
yeah, okay. So from C2 dash to C1 dash, we'll choose the blue edge, and then we'll choose E5,
Yeah.
and we'll choose this for sure because for C1 dash to T, C2 dash C1 dash has a minimum weight comparatively, right? Uh, yeah, this one like has minimum loss,
Which
because
one?
C2 dash to C1 dash will have a minimum loss compared to E5.
So C2 dash to C1 dash.
Will have a loss that is less than E5, right?
I've not associated a weight here, but it is like infinite.
Okay,
Infinite means you can take this edge as many times as you want in the flow.
so
Yeah, I should have told that before.
okay, okay.
So what I'm going to do is that redraw this again because I have made all of the red and blacks are completely mixed up with each other, and probably it is not clear which edge is what type. So I'm quickly just going to redraw and tell you on simultaneously what we just discussed. So C1, C2, so C1, C2. Can I just call them 2, 1, 2, 3? I'll just call them 1, 2, 3, 4, 5, 6, 7, 8. And the circle ones are, sorry, we have 9 cells. 9 are the black ones. We have a copy of every cell here. We introduced one start and one sink, and we said that for every white cell, the edge from the source to it is going to be an indirect edge. And yeah, so let me first mark them. These are capture indirectly edges, and then we are left with two other actions for every white. Other is captured directly, black denoted by black edge. Last one, I've made a mistake here. Yeah, so this, and the green edges in between which denote that don't pick, ignore. This is for same for everybody, so I'm just going to draw this. Now for the black cells, the first edge from S is a capture directly. The second edge from the copies to T is captured indirectly. Weights of these edges depend upon the type of the edge. If it is a direct edge, then it is Cij. If it is an indirect edge, it is Bij. If it is an ignore edge, it is Vij, which where the semantic is the loss. And then we said that we are going to connect every black cell with its neighboring white cells with edges of capacity infinite. So 1 and 3, 2 with, what was that, 5, 2 with 5. I'm just going to draw for one black cell here so that it is not cluttered. Other black cells will also have these blue edges with their neighbors. Okay, now we are saying that if we pick this edge, indirect edge, means if we are going to pick the cell C2, C1, C3, C5, C4, C6, if we are going to pick C2 indirectly, then our graph will ensure, like basically our min cut algorithm is going to ensure that its neighbors C1, C3 and C5 are picked directly. Okay, and why is that? Because if we do not pick, I'll number the edges 1, 2, 3. If we do not pick 1, 2, 3, like the direct edge, let's say if we do not pick 1, then what will happen? If we did not pick 1, then we can go from S to 2 to 1 and 1 dash and then T. Say if we had picked the indirect edge instead of the direct edge for cell 1, C1, then there would still be augmenting path from S to first, like augmenting path will be S to 1, 1 dash and T. Basically we are just going to take another action. So that, and while that is not allowed, and that will not also happen because that is only going to increase our loss. Basically the cut value, it is going to increase the cut value. So it is going to pick these edges 1, 2 and 3. The same is the case for a white cell. If an indirect edge like this edge 4 is picked, then the black cells which are in its neighbor C2 and C4 here, they will be directly picked. Now I have not drawn this for this. Let me just quickly draw neighbors of C4, not C3. Mm-hmm. 3. 4 neighbor is 1, 5 and 7. 1, 5, 7. So if we picked the edge S to C1, then and we have to pick the black edges for its neighbor C2 and C4, because if we do not pick the black edges and instead let's say we picked either the ignore edge or the indirect edge, red edge, then there will be path still for cell C1 via blue edges, because then we can go from S to 2, then C1, then 1 dash and then T. But if we take the black edge, then that path will not be there. So yeah, this is the final flow graph, and here we have seen what the vertices are, the edges are, what is going to be the weight of the edges, and we find the minimum min cut, which is basically the minimizing the loss, and finally we subtract that loss value from the total value of the grid, and that will be our answer. That will be the maximum score we can get. Is this, I mean, is there any point that is not clear? Or was it too complicated and I could not explain?
The rest is clear. I am only confused about the graph. Like the two claims that we have made, I am getting difficulty understanding them only.
Yeah, yeah. So, hmm,
Just trying to understand right now.
yeah. The way I understand it is that the minimum, so the min cut uh, algorithm. So, if we choose multiple edges for every cell, that is definitely not going to be the best case. That is not never going to be the optimal answer, because definitely a min cut is possible by choosing only one edge for each cell.
Yeah, I got it now. I think like it's like if we are choosing a cell multiple times, or we are choosing multiple actions, then the cost of those actions will also increase, and therefore the minimum value will not. I mean, the minimum value will increase, and that won't be
Yeah,
feasible.
yeah,
And what if there is like for some edge there is the cost of like zero? If we say
yeah. So if the cost is 0,
like in
hmm,
that case we can choose it multiple times.
mm, can we choose it multiple times? Cost, what's the constraint? Yeah, the
In
cost
constraints also we can
can
have cost
be
equal to zero.
equal to 0. Hmm. The cost is 0, then yeah, we should not. So probably we should not add edges with cost 0. Should be.
uh, if we won't add, I think that would be a worst case because like
Hmm.
they would be the best edges that we should pick for sure.
Yeah, yeah. So we should add them.
But I think then the direct edges will be chosen by themselves because that would itself be the best case for every cell.
The direct edges? Oh,
Will
you're
be
saying.
yeah, because if you're choosing them, then the cost will be minimized itself for that particular cell.
Hmm. Hmm.
So
Also, the Mm, so picking 0, making it 0 actually is not going to increase the flow, and I think the flow algorithm will terminate when we are not going to find an augmenting path with uh, flow greater than 0.
Yeah, that was I was thinking just right now that I mean, like if the uh, rate is zero, and then we'll itself just terminate the flow. I mean the flow algorithm, because we are not actually finding a path there.
Yeah.
Like capacity is kind of zero, so it won't run, and therefore we'll already have the min cut we can have, like the maximum flow that we can have.
Yeah, no more augmenting paths with non-zero
Yeah,
capacity.
and that way it will for sure choose the the uh, edges with the zero weight first. Like I mean the paths with the zero cost first, and then the others.
Mm, yeah, yeah, I think I also need to think about that. I did not give attention to that for earlier. Yeah, thanks for pointing this out. Yeah. Yeah, this problem was very challenging for me also. I've so I've also not done a lot of network flow problems. I hope I could um, explain the flow graph and what the edges mean, and why this flow graph is uh, actually satisfying the conditions that we were told in the question. So do try this problem. This is actually a problem on HackerRank. I will give you the link. I'll add the link, and do try this. Once you know how to form the flow graph, it's of course pretty straightforward. uh, Apply the next algorithm on this and get the min cut, which is equal to min cut value equal to the max flow value. Yeah, so are there any further questions?
Uh, and can you share some tips like how to understand, like how should we initialize the process of like understanding if a problem is min cut or not? Like it is very kind of annoying seeing it at the first place, and then it's not clear like what kind of a graph should we model.
Yeah, yeah, that is actually would I would also take some time. I also need to spend some time there, and probably after that I can give you a better answer, because I think it's so. First, you need to I think first we need to find out what the vertices are going to be. Then we have to, like in this problem itself or in previous problem, the either it can be a cell or it can be a combination of row and column, and so then choosing what the vertices are. Here we did not even choose a single vertex. We had two vertices for each cell. And then what the semantic of the edge is, what is it denoting, that we need to then, I think we need to give some thought about what a vertex is going to represent, what the edge is going to represent, and uh, how can then we model this as a, let's say, min cut. Now looking at a problem and deciding whether it is a max flow min cut problem or not, I think that we will be able to get only with practice. I feel that even with a greedy and DP problem, looking at a problem instantly, I think you, unless you have practiced problems, you cannot say that whether it's a DP problem or a greedy problem. It's not so easy, I feel. Sometimes we may think it's a greedy problem, while it's a DP problem we get some suboptimal answer, and we don't, unless we don't come to realize, no, the greedy is not, that greedy is not going to work here, we'll move to DP. Or we should be able to understand that we have to look at all the possible solutions, all the feasible solutions, right? Similarly, I think here also, yeah. So so here also I think if you solve a couple of problems, look at different classic problems, and for that you can refer to a good textbook. Initially, look at some classic set of problems where I think there will be some variation in what kind of vertices, what kind of edges, and what the weight of the edges, and how it is then modeled as a min cut and problem. I think after looking at a couple of classic problems and solving some problems on platforms for those and some similar, I think then probably it will become easier. But think of it like this, that when you first started solving DP or DP, let's say, it was not easy. So similarly, if you're just getting started with network flow also, and then similarly to that, you also need to again practice a couple of problems before you become familiar or comfortable with modeling the problem as a network flow problem. And yeah, for your exact question, how to identify the problem, if it is a network flow or not, I also don't have an answer. I think I myself need to spend some more time in this topic to better answer that question. Yeah. So hopefully by in the end of this course, let's say, I'll also try to spend some more time and try to answer that question.
Sure, thanks.
Yeah. Thanks for joining. I hope the session was useful. I'll post the link for HackerRank problem. Do go and try that. And yeah, so let's meet in the next session.